Okay, I wanted to download the Wireshark, uh, and we can try first with Wireshark and get some idea from the pretty graphical user interface uh, network sniffing program. All right, so I think I got already downloaded. Where is my Wireshark? Yeah, if you download your Wireshark and install successfully, then you might have the icon to have another version. I think this is the recent version, similar version as the one that you just downloaded. Okay. Uh, Software has been updated. Right. I think the version that you have is 1.12.8. Mine, I'm going to postpone. Mine is it's not way from that version. Mine is 1.12.7. So yours is 1.12.8, right? One version behind, but that is okay. Everything looks similar, I guess. If you want to capture the packets, then you have to first to define network interface. Um, so you have to see somewhere here in the capture menu. Then there is the interface menu. You can do it by Control I, and you can get the interface. And you can there are a lot of, I think, more than one interface available. Some interface from the hardware, some interface just the software. Okay, but anyway, if you see this, then you can see active interface. You do not have to choose all of this. If you want, you could. But if you see here, then I have one, the packets moving quickly. If you see this, then you need to click that interface. Okay, as you click, then there is a button, start button is clickable. If you unclick this, nothing, no interface is chosen, then this button is dimmed away. So you need to choose one of those, right? But anyway, some others, there is no packet traffic at all. So I want to choose this. And then start. Then packets coming in. So all the packets that you can see, overwhelmingly many packets coming in. So although this is a very good tool, very, very fancy, but almost impossible to analyze manually, right? It's not good tool for a real time. That is the reason we want to do the Python programs. All right, let me stop this. Of course, you can do some filter so that you can receive some packets that you want. Okay, you can filter by IP or source IP and destination IP. You can uh, even by filter by some keywords if you want. But up until that time, you do not know. You first define what it is, right? And then still you have uh, many packets listed. So what you need to do is, I want you to take a look protocol. There's a multiple columns, right? There's a serial number and time ticked from starting from 0. So you can convert this time to the real your system time. That is okay. And source and destination IP address that can be seen here, and followed by protocol. How many of you right now follow? Shivani, you virtually. Oh, you did that? Great. Stephanie, do you have Wireshark installed in your system? Have you heard of it? Edmondo, would you be able to help her? Where it can be downloaded? Well, I can bring up my. Yeah, it can be downloaded from here. www.wireshark.org/download.html. And simply install it and then click the icon to start. But if your Wireshark program needs to receive packets, then you have to choose network interface cards, one or more network interface cards. Interface cards can be selected by clicking the capture menu. Then you can see the interfaces. Okay. There you can choose one of those. That's what we did. So that we have the packets, and I stopped. As I said, the filter is possible. Some of the historical filter that you did can see, and also some expression. The Wireshark specific expression can be formed. There's an application specific. You don't have to memorize it. The point here is that I want you to take a look at the protocol column. Then you can see, you can scroll this up from the beginning somewhere. Then you can see UDP and ALP, UDP and ALP. ALP address resolution protocol, something like that, right? And some of the protocols listed here, but we didn't study all of those, but UDP particularly and TCP. So if you click UDP, excuse me, if you click UDP, look at the size, the length next to it. So click the one little bigger size. Okay, I do not know where it comes from, but anyway, it's a very strange. Look at this IP. Source. This kind of program is not really trusted, right? Source IP is not properly, well, we'll take a look at. Source port 63,807, destination port is So our destination. Okay, if you click the UDP, for example, then you can see there's on top the pane. In the middle, it it consists of three parts, three compartments from top to bottom. Top, you can see the series of the packets received by your the Wireshark. In the middle, um, it displays the content of that packet. So we'll look at that. And the bottom, where you can see the hexacode. Okay. I wanted to look at the in the middle pane, and from the top, it starts from frame, Ethernet, and Internet protocol, and datagram protocol, and data. This list is particularly for UDP. Frame as a whole is called packet. And then there's a Ethernet to source and destination information. Actually, this is this and the next is talking about IP. So IP version, and one below that IP data, there's a either TCP or UDP, but in this case UDP, followed by payload data. What happens here is that if I can bring up the earlier version of your okay, so this may help you to understand what it means. Okay. UDP protocol has a source port number and length and checksum and application data. In this Wireshark, correspondingly, the data portion here is one separate. These are all something about the data. And one above that, that is everything here. Source, port, destination port, length, and checksum. So if I unfold by clicking plus sign, then you can see that information. See here, source port. Source port is that, destination port, and then length and checksum, right? After checksum, there is data. This UDP header information is let me see if it is here. That is attached to the payload as it goes down along the network architecture, the 7-layer architecture. So let me see. Okay, yeah, this is a good example. So encapsulation from the top. See here your source program. So when you make your source program, which is a data payload, and you want to send. Then that payload traverse through this architecture from top to bottom, where there is a physical linkages. So as it goes down at the transport layer, then there is a header. First, the header is attached to the message. That you can see here. This is a payload. To this payload, from this transport layer, because this is a UDP header is attached to that payload. So all together, this and that together traverse one level down, where there is a network layer. When it arrives at network layer, then IP protocol is attached to it. IP protocol is attached to it. IP protocol has let me see, IP header the information as follows. This is UDP, this is TCP. It's not shown here, but in your textbook, if you turn to the section 3.5.3, which is the third page from the last. The header information displayed there, IP header and TCP header. I didn't put the UDP header, but in the next version of this, I will put that there. So if you look at the IP header, the first data from there is a version. I want you to look at here in this Wireshark. Then the first data, as you unfold this, the first data is a version. Now this is a version 6. And followed by let me unfold this. That is it. And let me unfold this. Followed by IHL, I guess. Followed by total length. So third one is a total length. And then one next line starts with identification. So identification there is, it says a UDP, and flag is 1. There's a flag offset altogether. And after that, well, it goes even further. And the last 3 lines, it says a source and destination. It didn't display all somehow, but if you program this the way that I showed in Python, then you can see all detailed information. Okay, this Wireshark skipped some information, so it doesn't allow you to read. But actually, you can read it by program. Okay. So as data comes down all the way to the physical layer, then you have a frame header. I mean frame is, this is called packets. Packet is formed. So packet is the data that has packed with all the header information. Header information is generated from each layer. All right. and that packed message now travels through your network connection. Some network device equipment needs needs to identify the information, then it unpacked a little bit. For example, at the switch system, it unpack to the link layer, so it needs to know some frame information. When it reaches the router needs more information, network information, which means router says I need the source IP and destination IP. So packet as a whole, there's a packed information, doesn't show any such data. Therefore, when it comes to the router says, hey, I want to open this. So router unpack the packets up to the network layer, which means it needs to understand the IP data. All the IP data, that's IP header contains the total length of the packets and source address and destination address and so on and so forth. Okay, so that's what you could see. Similarly, if you pick TCP, there's some TCP. I want you to pick a bigger size of TCP. Small size of TCP, it has some shake hands information. I mean, before it send the data, then they need to first to set up connection. Remember that UDP doesn't need the connection, so we call that connectionless. Doesn't need any, for example, identify your destination, and your destination needs to acknowledgement, and then you need to set up the network before you send the data. So at this point, I guess this one has IP, yeah, typical IP. So if you look at this, then from top, there's a frame information, and then Ethernet, there's IP. From the link layer, you can do Ethernet information. At the network layer, you can get the header information about IP. At the transport layer, you can get transmission control, TCP header information. So by clicking the TCP, then you can see exactly the information that you could see here in your slide that I posted. Then there is a 16-bit of source port and 16-bit of destination port. Source and destination IP is known by network layer, so that IP header contains the IP information, but header attached from the transport layer contains the port information. So now this TCP has started with the port information. If I unclick one above there, so IP, then it has source information and destination information, right? So one below, then we have port information. So port information, and then 32-bit of sequence number. 32-bit of sequence number up to this, and then acknowledgement number, and all this, all detailed information can be, some information can be found here. Let's say some acknowledgement and checksum. Where is a checksum? Here there is a checksum. it's about that. And then receive windows, yeah, some of the Windows information here, receive window, and then this all information UAP all SF can be found somewhere here, right? So for example, checksum, if you click checksum, this is checksum, right? Checksum, then the bottom there is a 99 and 00 in hex highlighted. So those 2 bytes long data is about checksum. If you come here, checksum, whole length is 32, so half of them is 16 bits, which means 2 bytes long data about checksum. That's what you can see here, 9900. So if you convert this 9900 to binary code, so that you can understand how error can be confirmed. So in this case, there is no error. It should be confirmed in TCP, right? Because TCP needs to send the data properly and completely, which is not the case of UDP. So UDP does not have this. All right. So all detailed information like this can be done in our program. So let me bring up our book. Okay. If you see the book here, then you first create an object of a socket. So there is a socket constructor that can receive 2 or more input parameter. First parameter is the family of network. So the network family that you need to use is AF underscore innets, inets. If you use another platform, then another family is needed. And for this socket sniffing, the packet sniffing, we need to read it by sock row. When we set up client and server program, we use the sock underscore stream. This is the type of the network socket. But in this case, we want to read the data in this type, raw data, and then followed by the protocol. Protocol that we want to use here is IP. So instead of this IP, you could do TCP or UDP. In this example, I want you to do with the IP. If you sniff the IP information, then you can see not this, but the one that I showed in the textbook, IP header. So there's a version information and IHL and whatever that follows, right? So the program should start in this way. As I described here, these are the steps. The first step is to acquire network interface. As we did for Wireshark, we need to define the network interface and then create an object of a socket. How can you create an object of socket? We can create it in this way, as I just explained, right? Socket constructor, which can receive the three parameters: the network family, network type, and network protocols. So properly um, assigned, and then bind the socket object to the network interface. So you have an interface and then socket object. Now you need to bind them. So your socket object is bound to the interface that you chose. And then you can unpack the data to identify or interpret the way that you can use. How can we see those all detailed information? As I said last time, if you go to the website www sorcery, right? Networksorcery.com. It's a networksorcery.com, and click RFC sourcebook, and then there is a IP protocol suites, and there is the Internet Protocol IP. Then it describes all details. IP header has a version and IHL, for example. Then version and IHL together are packed in 1 byte. So if you have 1 byte, then you have to split the bytes. High 4 bits for the version and low 4 bits for IHL. How can we split the bits, bytes? How can we split the bytes so that you can understand the first 4 bits and last 4 bits? That is exemplified in the source code. It's a little bit of a coding issue, right? So first of all, 4 bits is talking about the version. If you identify that gives you number 4, then you can say, oh, that is IP protocol. And then the lower 4 bits talk about internet header length, okay, and so on and so forth, all the down, okay. So if you click any one of those, then you can see detailed. For example, header checksum, then this header checksum, 16 bits. So you can capture those 16 bits information about checksum so that you can analyze it. You can manually see if there is any error or any corrections. So back to our source code. So line number 3, network interface is set. We call that host. We can get the network interface from the function of a socket. There's a function called the get host by name. If we enter host name to that socket, then we can get the host interface information. And then line number 6, we construct an object of socket, and then we bind interface to the sockets. And after that, something that we want to receive this size of data. Receive packets. Yeah, up to this point, we simply receive the packets. Next, let's see. This is for Linux. This is for TCP. So I want you to do this up to this, and then we will look at the Linux and Linux for the TCP data, TCP packet data, and also UDP. UDP can be done on Windows system also. Finally, I listed here the source code to identify, for example, the version number, and then internet header length, IHL information. So actually what you need to do for today, I want you to practice the example 3.52. Okay, once you have some packet information, then we can unpack, okay, a little later. Okay, let's do that. All right, if you do successfully, can I take your attention? Let's move. I think everyone has, right? With this, then there is a, this is outcome from your package, right? There's a lot of things that you have to do, but at this point, the program that you just implemented is a one-time packet, right? Didn't do any further, but you can do it on your own. But more importantly, if you see this packet header, IP packet header, it's not readable, right? It is packed. So we have to unpack in order to identify this. So so I described a little bit there. So what we need to do is, I think you did up to here, right? Packet header. And yeah, IP header. Right, IP header. Whatever packet data. Is it what did I say here? Let me see. Yeah, TCP data or IP header. So let's say IP header. IP header. That's what we received. And this returns this ugly the hexacode. I mean, it's not really hexacode, it's a byte code. Okay. So we have to unpack it, otherwise we cannot see it. Before we unpack, we need to have the first, this itself is in the list. So we need to split the first item from the list. We call that data. And that data we have to unpack. In order to unpack, you have to import struct module. And this IP header data has a longer, but first 20 bytes. That's what we want to capture. First 20 bytes, which means this is a TCP, right? If you look at the IP from your text, from the top, so each row is a 4 byte, right? So how many rows? 1, 2, 3, 4, 5 before option and padding. So 20 bytes. If you want to identify, if you want to interpret 20 bytes, then you need to say here 20 bytes. I want to read only, remember that this is list format, and I want to read from the beginning 20 bytes. The index is starting from 0, so usually you can put here 0, but that is optional. 0:20, then there is a 21, right? 21 bytes. But the last one here, remember that? We want to capture the number up here last. That is not included. So we want to up to the number 1 before the number that you specified here. So what it does is that it capture the first byte, so 0 to 19. 0 to 19th means there's 20 bytes, right? 20 bytes long. If you count this, there's 20 bytes long. For those 20 bytes long, how can you read? You read 20 bytes long as one data or any specific data. Then you need to come back here. And you cannot read any smaller than byte. The minimum, the size of data that you can unpack is the byte. So what we did here is before byte. I want to read the first byte. And then second one, also I want to read the byte. So that I specified here 2 BB, which means I want to read the byte and another byte. And after that, total length. The size for the total length is 2 byte long. So that I specify H. Okay, then I cover the first row. And after that, another 2 bytes long for identification. So another H.
So the H stands for 2 bytes?
2 bytes. Before 1 byte. Right. Where can you get it?
H equals 2B.
Yeah, 2B. So we did that last time. yeah, you did something else. Yeah, when I explained this last time. To get that, let's see. Is it here or no? Not here. You need to open up the struct module. So Python struct, then you can get the information about struct. Okay, here when I click this struct, here in this website, if we want to read data from network, then when you unpack, it starts from the exclamation mark. So in the source code, it starts from exclamation, followed by the size to be unpacked. If you scroll down a little bit further, there's a format characters. Format characters. Uppercase B, so unsigned character, we want to read it integer, size of that is 1 byte. That's what it is. And then uppercase H, size of that is 2 bytes. Okay? And there's another one, if you want to read as a string, then lowercase s for string. So back to our source code, the format to be unpacked in this way. Look at my highlight here. The first 1 byte for both the version and IHL. Next byte is the second bit for type of service, and next 2 bytes for total length, and next 2 bytes for identification. After that, we have flags and fragment offset. Flags is indicated by 3 bits only. Remember that, as I said, the minimum size of the data that you want to unpack is a byte. So we cannot. If you buy byte, then it also split the fragment offset to save all, and to interpret it properly, we have to read 2 bytes. Do you see that? Let me bring here. What I mean by that here is this is 2 bytes. This is 1 byte. This is 1 byte. This is 2 bytes. So therefore, with the format of data to be unpacked is starting from B, uppercase B, another uppercase B, and then uppercase H, and another 2 bytes for identification, uppercase H. And when it comes to here, then this is a little bit tricky because first 3 bits for flags and last 13 bits for fragment offset. So we cannot read 3 bits. We cannot read 13 bits separately. So best way that you can read is 2 bytes together. Once you read the 2 bytes together, then you can split it. The way that we would do here, first to 1 bytes anyway, then we have to split. We can apply that technique here. We'll do that a little later. So when you see that, I think we have up to here or there. Okay. After that, 2BB, which means, yeah, first bit is time to leave, another bit protocol, followed by checksum, which is 16 bits. Checksum code always is 16 bits, 2 bytes. So back here, there's a 2 bytes H. After that, 4S and 4S. After this checksum, source address and destination address. S, there's a string. String is string is you have to, this is 1 byte, so you have to specify how many. So actually this is 4 byte long for source address, so that you have to do 4S followed by another 4S for destination. If you do this, then you can read up to where? Up to here, destination address. If you want to read further, then you have to do, for example, 2 byte long and another 1 byte and combine them together. And the last 1 byte is for padding. After this padding is delimiter between the header. So IP header, one before IP header, we have a TCP header, right? And so on and so forth. So in this way, it is unpacked. So unpacked data. What this unpacked data has, it unpacks so that in the way that you have here, BB, HHH, BBH, then the first B can be accessed by the index 0. As you unpack, then outcome of that unpack method is another list. So first item of that outcome list is accessed by index 0. If we want to identify the second byte, for example, type of service, then what do you need to do? You need to have unpack data number 1. Okay? And further, total length, next item, which is indexed by 2, right? Third item. You can go further and further, but I want you to understand here, how can we, for example, they are combined together? Because we can read not by bit, but byte. So we read together in 1 byte. Then we need to split it as 1 byte. The first 4 bits for version. This is a version. This is the data. You don't have to say it. Yeah, version and IHL. Version and IHL together. This is 1 byte. Okay, that I need to explain that a little further here. Here. Let me see if I have that here. I explained this already, and this. Somewhere there. Okay, let me explain it here. See here, 1 byte. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, so first 4 bits, this is a version, and next 4 bits is for header length, IHL. Right? So we have to split that. How we could do is, right now this is, as a whole, this is called, I think, a version and IHL. Let's say version and H. Okay? Version and header length. In order to get this information, if we read, then we have all the information, right? But if you want to read this only, then what you need to do is if you there is a bit operation like shift. This is right shift, and if you have the other, then this is left shift. If you shift this 4 times, look at this. There's a shifted. So shift this 1, 2, 3, 4. Then everything here can be outside that boundaries. Only what you have here is it is now this is a low bits, as if there is a another upper bits like this. Only that you can read from there is this only. See here, I want to shift to right 4 bits, then everything shifted. So 1 byte looks like this, not anymore this. 1 byte looks like this. So that you can read completely those 4 bits as you shift. As you shift to that and then version, then you simply print it, version. Then you can see the version number. And how can you get IHL as a whole, which is version underscore IHL. Now we want to make it bitwise operation, bitwise AND operation. For hex, I want to end the operation by F. So what I can get from there is back here. Suppose if I have 1 0 1 0 0 1 1 1, what I want to capture for IHL is this 0 1 1 1, right? If I want to make bitwise AND operator, which is here. So 0x means that's hexacode, followed by F. F is F means 1111, right? So we have here 1 1 1 1. This is not good. Number is not really, which means there's a 0 0 0 0. We have AND operator. What is the AND operator? Only if they are both 1 1, then it returns 1. Otherwise 0, right? 1 and 1 is 1. 1 and 0 is 0. 0 and 1 is 0. 0 and 0 is 0 also, right? That is the AND operator. So if you apply F only, F means 1 1 1 1. The first upper 4 bits is 0. So this is nothing but 0, 0, 0, 0, 1, 1, 1, 1. We apply that. And the operator then, anyway, we can kill the upper 4 bits. Whatever number that is, if we AND operator with the 0, then it can be automatically 0, right? And then the last 4 bits, we still reserve it by multiply by 1, right? So 1, 0 means 0. 1, 1 means 1. 1, 1 means 1. 1, 1 means 1. So when we read this data, that returns only the last 4 bits, right? Because we removed the upper 4 bits by multiplication. Not really multiplication, it's the AND operator, right? So we achieve the data that we want to. Right here. So we did the AND operator. The version IHA is everything. The first 1 byte. The upper bytes can be obtained by shifting to right, and then lower 4 bits can be obtained by multiplying bitwise AND operator with the hexacode F. Then we will get the size of length. Okay. Any question about this? A little bit of tricky but very straightforward. No question? I leave it here as is, so you can try to understand why we first do right shift and the next one is by bitwise operation. Okay, and then I want you to try. You can add few of lines, then you can get the information at the moment, right? So the outcome of your previous program is all unreadable data. Now you can read. You can unpack and read and interpret. The way that interpret, there's two things. The way that you can unpack, you have to read the struct manual. The way that you interpret, you have to go back to sorcery.com. If you come to sorcery.com, then, for example, the version number, if it returns 6, for example, then that is one of these. SIP, Simple Internet Protocol, SIPP, Simple Internet Protocol Plus, and all of this. If it returns 4, then IP and Internet Protocol and some others, right? Practice. So version, in my case, version 4. What is your version? Version number? Anybody try? So in your program, if you want to do even further explanation, then you need to go back to sorcery and then another conditional statements. You can say if it returns number 1, that it means something. Number 2 and some, and number 4, then you can say that it's IP and Internet Protocol. Number 6, then SIP or some others. You can explain the way that you can see from that web page. Okay. In such case, by doing so, you may have more detailed information. There's no further fine granular information than this. By doing this, you can get all seamless information from the packets. Although some information is not hidden from Wireshark for some reason, but in this case, we can unpack and read every single bits and bytes. Okay. All right. What I want you to do is, so far we looked at these two data, right? And next one bytes is for the type of service. So how can you get next one bytes? Remember that back to here. So first bytes we handle it. Second byte is what was it? No. After the IHL, what is the type of service? So we can get the type of service. This first byte can be obtained by this index. Next one bytes by obtained by which index? Number one. This is number 0. Index 0 is the first item. If we do index 1, then second item. If we have index 2, then another item, which is 2 bytes. So type of service can be identified by, very simply, if you put this 1 and read and assign to another and print, then you can get the type of service. Only the issue here is that whatever the number that you receive, what does that mean to you? Then you need to go back to here, type of service. Come back here. If you have to identify one bit in binary code, if it is, for example, 001010, then it means that is assured to forwarding 1111 type of the transmission. What does that mean? Then you have to report to request for comments. This is a document. You need to click, then you can go to some of the documents and you have to read what it means. All right. So it's a lot of interesting stuff here. This is a real research, right? Although there is a straightforward and all already defined, but maybe new to you. All right. Not many universities get into this level. If you look at if you search the website, then only the few best schools. So we are at that level. You have to be proud of it. All right, go ahead. I know we left undiscussed, left something undiscussed. Multiprocessing and multitasking and multi-threading. Those are all the related issues for operating systems. When we discussed about network sniffing program, network sniffing program actually needs multiprocessing and multi-threading. What it means is that packets coming in continually, and your Python programs cannot handle the incoming packets in a sequence process. Maybe possible if your incoming package is not overwhelmingly big, and if your computer runs so fast, maybe so. But there is another technique that you could handle in the following. There is a data structure called Q-U-E-U-E. And also there's another big research area is called queuing theory. Some mathematical application discipline. That queue is also one of well-known data structures. What queue can do for you is it can hold some data in a fashion of first come, first served. So you might create multiple queues. One of the queues, the first thing that you can use is incoming packets. When packet comes in, then you can put it in a queue. Packet continually comes, so queue can hold. Meanwhile, another processor hold the first entered packet and then unpack and process. When it's done, then pick up another packet. Pick up another packet. If it still slows, then create another queue. Put it there for a while. And then another process can hold it and process it. So there may be a lot of back-end processes available, but still can hold all the packets. That has been described in that in my I think slides. Those who are interested in may be able to read and understand and enhance your programming. Okay. Instead, we are going to jump into the last module. Last module of this class is the system issue. In computer science, there are two major systems that we all deal with: operating system and database system. They are very similar. System-wise, they are very, very similar. So those who study database can understand the operating system, but not all operating system experts can understand the database. Can anyone think why? Some of you know operating system, some of you know database, right? Even the Mercy database course doesn't touch, as far as I know, the system issue much, but it is more data modeling issues, which is highly discussed in business school. Business school also deals with some databases, right? But computer science, we overcome that issue. If it is not efficiently running on a system, then it's not the computer science issue, right? Everything should be feasible on physical computers. There's a whole concern of computer science and also our cybersecurity program. But anyway, so operating systems. So we will look the introduction of operating system. This covers overview of operating systems. We're not going to get into the deeper level. Not really needed much, right? But while we handling the operating systems in Python, anyway, you may be able to learn a little more than this. So, what is an operating system? Operating systems is nothing but a software packages. It's not hardware. It's software. What is a software packages? It's a program. How does it is it different from the program that you do? Exactly the same program, right? So all the collection of programs that can handle for majority of users desire to perform. So operating system is a program that acts as, it says, on intermediary between a user of a computer and the computer hardware. Think about this. As you do scripting, Python, many times you do print statements, right? Print statements, unknowingly so far, you simply use it, therefore you can see the some of the messages on your terminal. Terminal is the hardware, right? Somehow your program handles the hardware. Although you didn't much, right? But apparently, locally, your simple program can handle. How is it possible? Sometimes you are not really super user of your system. Still, you can handle the terminal or keyboard or external devices. Those are all things should be done by super user, right? Not arbitrary casual users. How come it is possible? So in operating system, there is a multiple layer. On top, application, like your Python program. In the middle, there is a operating system. Could be Windows, could be Linux, and Linux or Linux program particularly has a kernel portion, which is a core engine of your operating systems. That kernel of Unix operating systems also embedded into your smartphone. We call that microkernel, right? So iPhone and Android phone has that microkernels in it. Microkernel is core portion of operating systems. On top of that, some other management components. Those management components here in this slide. It has, for example, process management, memory management, storage management, protection and security management. Why didn't you tell us? I already made some progress. This is I came back from where I was. I was here. There's a program. Okay. So kernel On top of the kernel, we have a multiple management programs. But here, kernel. So what happens here is that we have a kernel and multiple management. Everything is called operating system. On top of this, we have application. Okay. Underneath this, we have a hardware. If we do Python program, .py, somewhere here you say print. Statements. And some of the management is the external device management. Okay, some of management. Let's say that is external device management system. Then your print statements should request to this guy, hey, I want to use the terminal. Then this guy touches the terminal so that you can see it. Your program does not contact directly. So there is a somehow switch. We call that context switch. Okay. Context switch is implemented in stack. There's another elementary data structures, as I introduced to you, the queue, right? Basically queue and stacks. Queue is served the first come, first served based. Stack, first come, last served. So last come, first served fashion is implemented in a stack data structures. It's simply, if you stack up something on top of another, then only that you can access is the last entered, right? And the second last that you can pop from the stack structures. Context switch is a stack implementation. So for example, this program itself is the bottom of that stack structure. That program, py. And then there is operating system needs to be involved. This is a print. We have to finish these print statements in order to finish entire Python program. This is a stack, right? You cannot do, oh, let's finish Python first before print statements. Print is within that Python. How can we handle that? We can handle it by this stack operation, stack structures. But anyway, so operating system is a program. So operating system goals is to execute user programs and make solving user problem easier, make the computer system convenient to use the computer hardware in an efficient manner, right? So first item is very clearly understood. Third one, some utility programs. So some operating system can handle, for example, defragmentation of your storage disk, right? Fragmentation and defragmentation. Fragmentation, good for to utilize your storage. Defragmentation is good for to reduce the access time, delay time. When you retrieve data from your storage to the main memory, right? If it is not, then when you click some application program, it takes long to load. Your operating system is not functioning well, then functioning well so that you can apparently see time delay, open up that program. After you click that program, then storage manager has some issue, right? Like my laptop has storage manager issue. I don't complain because there is Microsoft products. It happens always. This is a computer system can be divided into 4 components: hardware, operating system, application program, and users. Right? We're going to deal with the operating systems here in this module. We're not going to do application program. We're not going to handle users, not even hardware. Right? Hardware is not the subject of computer science. Maybe hardware is the subject of cyber security. Cyber security needs to do anything where there is a cyber threat. Those 4 components can be stacked in this way from bottom to top, that you can see computer hardware, operating system is running on top, which can solve application programs. What operating system can do is to do you just want to convenience, easy of use, good performance, but don't care about resource utilization. User really don't care. Well, user cares, but there's nothing that user can do. So we rely the operating system do something for resource utilization. Operating system can share the computer, some workstation servers, and very simple stuff. Operating system is a resource allocator. Operating system is a control program. Not only that, a lot more, right? Resource allocator manages all the resources and decide between conflicting requests. If there are multiple requests for the same resource, then you have to control that. Controlling program controls execution of a program to prevent errors and improper use of the computers. The definition of operating systems. Okay, one program running at a time on the computer is the kernel. Kernel is a core engine of the operating system. Everything else is either a program, system program, or application program. So on top of the kernel, you have operating system packages. Top of that, application. As the computer starts, bootstrap program needs to be first loaded. Think about this. Hardware, everything is hardware, right? If computer is turned off, everything is hardware. Soon as you turn on, soon as power is supplied, your computer is booted and ready for you to use. How come it is possible? Basic idea that we all understand is anything that you want to do on your computer should be first loaded on the memory. Memory. I'm not talking about the storage. Memory. Memory is like RAM, right? Operating system stored in your hard drive, hard disk drive. Operating system, one of the operating system function is to load some data from storage to the memory. So there's a memory management and also storage management in between. All such things can be taken care of by operating systems. At first, but operating system is stored in the hard disk drive. There needs to be somebody bring that operating system up to the main memory. After that, operating system can handle all the rest. But there is something that needs to do that keep layer into the computer. Who could do that? There's a bootstrap, right? Anybody here originally cowboy? Right. Cowboy is if you sit on the boots, then you have to pull with that bootstrap, right? Like this. That idea is called here in the operating systems. Bootstrap program needs to be loaded. Who loaded that bootstrap program? It is in ROM. 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 ROM contains bootstrap program. Then who loaded that bootstrap program into the RAM? No, the ROM itself is similar to RAM. So it can do. As it is supplied, power supplied, it works, right? Then how do you know where there is a RAM, ROM, all such things? They should be first checked, right? It's called the post checking. Power on self-test, right? Thank you. Yeah. So first when you turn on, then post check first. Oh, it doesn't mean that it checks all the storage information, how many partitions and the size of RAM or ROM. It doesn't do that. Only the existence. If there is a keyboard, if there is a terminal, okay, first it check. And then go to RAM. If there is a RAM, then RAM program is running. RAM, unknown. Yeah, ROM. Whatever in the ROM being executed. So ROM where there is a bootstrap program. What it does is that bootstrap program access to, because you already know there is a storage by post checking. And operating systems is usually the first few bits. So it reads the first 512 bits. We call that master boot record, right? So if I read the master boot record, first 400 bits is doing something else, and then there's a partition information. So look at the partitions and know the bootable parts, bootable. Okay, so bring that information into the main memory, and from there, then operating system is being executed. Okay, that is startup procedures. Computer system has one or more CPUs and device controllers. Any device, if you have and connected to your computer, your host, then there is also a controller. Controller is also maybe sometimes hardware involved, but there is a pure software for device. We call that device driver program. If you plug USB, then there's a USB driver. So USB driver handles, right? USB driver knows the port where there is that hard drive connected. So this driver there's some other mechanisms, right? Polling mechanism or interrupt mechanism. Some other device, if you do some program, then interrupt program may be needed. So that interrupt, if some device driver program handles device and device sends some data, then this driver recognize data coming in from the device, then this driver interrupt the operating systems. Each driver has different priority of interrupt. Some driver has higher priority for interrupt, some lower. Usually print is in the middle, print process, print driver. Like print choice device, then there is a printer driver. The software needs to be installed. Another driver or interrupt, the highest priority interrupt is from the keyboard. If we are talking about the Windows, Microsoft systems, right? It's called the Control Alt Delete keys. As you press that button from your keyboard hardware, then it generates interrupt. That interrupt has the highest priority, so it holds all the executions. You know that, right? It's called, what is it? If I do this, then yes, task manager. So task manager is usually the highest priority of interrupt. But anyway, so there may be one or more CPUs. So you have a memory. Anything that you want to, let's say this is disk. There is a program. Your program is stored here. If you want to execute it, then this program first loaded through that controller in your memory. So that program is in this memory. Okay. According to some order sequence, this can be handled by this CPU. Anything that you want to do, that should be in the memory. Therefore, CPU can execute it. Okay. I/O devices and CPU can execute concurrently. Yeah, long time ago, this was not concurrently. So CPU should wait. But now CPU runs by itself. Why? CPU runs so fast than I/O access, right? I/O access, a lot of delays. So there is a context switch. So one program and another program that can be interleaved. So it is very naturally concurrency is possible, right? Piece of data runs, starts, and time sharing. Therefore, there's a concurrent. Concurrent is not the same as parallel processing, right? Concurrent means you have a one sequence, but you can have you want to handle multiple different programs. Then you need to handle piece of program or program one, piece of program one, another piece of program two, followed by another piece of program three, followed by second piece of the program two, followed by second piece of program one, and so on and so forth. So chunk of the program or processes can be handled by one CPU, one sequence CPU. It's a concurrent. It's a concurrent processing. Parallel processing is something different. You need to have more than one CPUs. Okay. Each device controller is in charge of a particular device type. So you have, if you have a printer, then printer controller there. Each device controller has a local buffer. For example, if your keyboard, you keep typing, then there is a buffer, like a queue, already implemented. So as you type, then before it is displayed, it stays in some buffer. Usually, currently, because of the high tech, your typing speed doesn't reach the limited size of buffer, keyboard buffer. But long time ago, if you type so fast, then buffer full, so waits a little bit. All right. CPU moves the data from and to main memory, to and from the local buffers. So once the device sends the data, then there is a buffer. Buffer holds the data. But reason we send the data to computer is, and also if it should be handled, then it should first be loaded in the memory. Therefore, operating system handle it. One of the handles by operating system is to save that data in the storage systems. So first it comes into the main memory. I/O is from the device to local buffer of a computer. Device controller performs a CPU that has finished its operating system by causing an interrupt. Okay. Microsoft operating systems use a lot of interrupt programs. If you want to build a new device, then it should generate interrupt. Otherwise, your operating system, your CPU does not understand what's going on out there, right? CPU runs by itself. So your interrupt program should wake him up. Hey, I am here. Can I interrupt you? Then CPU understands, oh, there is some request. So according to some schedules, that interrupt can be taken care of. If you do interrupt programming, so excited, but I'm not sure. So more exciting than network unpack program that we just did. Anybody had a headache of this? If you have some excitement from this, then you can get to some interrupt program. Okay, that's a system programs. There's no lower level than system programs. Okay, we do not have systems except the best schools. All other schools do not teach systems program. Don't need, right? Your concern is the application program. My concern is application program too. Interrupt program is only for those who needs to involve in enhancement of the system itself, right? But they do not have interest on the application. So each one has different in different direction. Polling and vectored interrupt system. There's two kinds, right? Polling is this. General idea is this. There are a lot of requests available. So I'm CPU. What we can do is, if I want to take care of, then I can say, hey, do you have any issue? Do you have any issue? Do you have any issue? That's a polling system. Another way is that, yeah, I can handle, I'm ready upon request. Then you can request, then I can respond. Basically, two kinds of interaction is available, right? Personally, I like interrupt interaction. Even in lecture, I want to interrupt so that I want to receive questions from students rather than I need to check by saying any question or any issue. Did you do this? Right? I want to keep going, keep move forward, and if you want to interrupt, then you can raise hand and hey, stop there and let's talk more. Right? In real world, these two kinds of interactions are always available. Um, train system. I can compare the train system. When I came here first, it was really different. It's not really shocking, but it's different that I recognized in the train system. It's a passenger interaction. In Asia, particularly Korea, then train stations, passengers, each train station is completely blocked. So if you want to take train, then there is a gate, and station officer stand there and check. So when they check the tickets, and tickets punched at the gate of train station. Once they get in the train, then there's nobody. Okay, only a few guys, like train conductors is patrolling back and forth, right? They don't check your tickets and they don't care where you stop, where you it goes for, right? That is interrupt mode, from my understanding. American system. Train station is not really completely blocked. You can access. You can walk into the railroads. You can access a platform from anywhere, right? Always open. You can get on the train, any train, right? If you do not have a ticket, then you can purchase ticket on the train, right? It's completely prohibited, yeah, if you do not have tickets from the beginning. If you sit on the seats here in American train, then conductor comes to you. Do you have a ticket? Let me check tickets. Do you have tickets? Do you have tickets? If you don't have a ticket, you should buy it, right? There's a polling system. This is just an example. So, which one is some pros and cons, right? Some trade-offs. If you have a smaller number of devices to control, then polling is possible, right? If you have a smaller size of a class, then I can, like this class, then I can check. Hey, did you do this? Did you confirm this and that? Still efficient, right? Let's say if you have a very large classroom, like almost all state university, the low-level class, then 100 and 200, 300 students takes class from one instructor. In such case, polling is almost inefficient, right? Instructor keep moving. Instructor. Interrupt still possible. If there's one student that back row and raise hand and ask a question, still okay. There's interrupt mode, right? Same thing in the operating system. Okay. 10 more minutes. Then we'll stop. This slide compares the holding time between CPU and device. It's not necessarily external device, but any device. Keyboard on your laptop, well, desktop, that is external, right? Anyway, that is device. CPU, between CPU and device, there is some time sharing, right? While CPU is executing some of your program, because CPU is busy at this time, then CPU and I/O separately running. There's some statements that we already looked at that, right? Where is it? Yeah, yeah, concurrently. So concurrent program is concurrent execution is nothing but time sharing executions. So while CPU is handling, then data is transferred to the memory. When a memory has all the data, then CPU now access that data already loaded in the memory and handle it from here there. And meanwhile, concurrently, data is still accessed. I/O structure. There is some mode. The controlling. Control returns to the user program only upon I/O completion. This is an explanation of this slide. Okay. After I/O starts, which means here, after I/O starts, right? I/O starts, then this CPU is running. Wait instruction idles the CPU until next interrupt. Wait loop. At most one I/O request is outstanding at a time. No simultaneous OS processing. So one CPU here, and then multiple devices. Then in order to be processed by CPU, they should be in memory, right? So there is a fetching process. Data should be fetched from the device. Device can be like storage, device can be keyboard, device can be a network, whatever, right? So when it comes to some data available and ready to be processed, then this data interrupt the CPU. And CPU understands, oh, there is a data that I need to handle. Meanwhile, other data should be idle and waits. Other data should wait while this is being processed. There's some sequence. We're not yet talking about parallel processing. We're talking about concurrent, one timeline. But how can we maximize the process? That is what we are talking about right now. Okay. And also, sometimes your CPU needs to handle the external external hardware. Then the kernel has system call. So your program needs to access some external device like printer. Although your program has only, for example, print function, or in Java, you can say system.out.println, you didn't do anything about handling this printer, but that's statements. Internally, this is interpreted and therefore call system program. We call that system call. It's like interrupt. Then this system call look at the device status table and to see if it is available and where it should go, and then go to proper device to solve this application program. That's what they do. And also storage structures. There are all other management issues already implemented. So we'll continue to this after Thanksgiving. Yeah, with some of Python execution, how Python can handle some of the operating system. Okay, interrupt rather than polling. Any interrupt? If I say any interrupt, it means polling. Okay. Have a good weekend and have a good Thanksgiving. Now we have interrupt.